Swayam Prabha. Digital India. Educated India.
Okay, dear students, so today I will start again the signal amplifications and this amplification strategy for biosensing applications. So last class I taught you how to amplify the signals using different kind of signal amplification strategy using some chemical. So let's now show you different kind of amplification strategy and use them for biosensing applications. So main concept I will cover today, mainly the types of redox cycling that we want to use, and we will cover the biosensors using the redox cycling amplifications. So main keywords for these lectures you can search also like redox cycling, electrochemical redox cycling, signal amplification. So they are the main keyword for this lecture. So the redox cycling, what is the oxidations, what is the reduction reactions, that I already told you at the last class, but just I want to summarize. See, if you have a redox mediator, like if you see that Fe2 plus, then if you want to oxidize it to Fe3 plus, means you have to release one electron, right. So for that see E minus, then this process called the oxidations. Now if Fe3 plus to form the Fe2 plus, then it can accept one electron and form the reductions. So when these oxidations and reduction process happen simultaneously on your electrode surface, that's called the redox reactions. And redox cycling means, so on your surface this species, oxidized species or reduced species will be reproduced cycling way, and you will get the signal amplifications, because these cycling reactions can reproduce and can means accumulate this on redox active species on the surface, and it will help the many electron transfer on the surface. Okay. So let's that concept I already told. Now let's come to a example. After giving some example, then I will come the names of the different redox cycling, so that you can interpret or you can design how redox cycling you can use, and you can design by yourself, like this cycling or these reactions can be useful for signal amplifications for biosensor, that you can try. Okay. So here you can see this is a this surface, you can see this is a screen printed glassy carbon electrode. So on that this is just a transducer, a electrode surface. On that surface so you can see just to be modified using some nanomaterial. So this surface, on this surface we want to use some redox cycling reactions. You can see here this PNP, this is just nothing but a para-nitrophenol. Para-nitrophenol means this one, this is NH2. Sure. So let's remove this one. Right. So see, so we are using a redox species, that is the para-nitrophenol, and this para-nitrophenol will take part in the redox cycling reactions. So para-nitrophenol, nitro means NO2, right, NO2, and nitrophenol means OH, right. So this species can form, this is like NO2 could this para NP nitrophenol, this can be, see, this is actually oxidizing on the surface, means nitrophenol will form like the oxidized species, it will form on the surface. So it will be O, this one, means it can form like quinone, or maybe it can form also in the oxidized species in the intermediate, and this kind of the intermediate step also it can form. Means in this means oxidized and reduced form, we need a reducing agent. What reducing agent we can use? We can use like a T-shape. T-shape is a reducing agent. This is the structures of the T-shape, and see it is reducing, then again come back to this nitrophenol. So, this here is a chemical reduction process. This is a chemical reduction. Okay. And here on the surface we are actually oxidizing, right. So, here oxidation happen on the electrode surface. See, so this oxidation actually happen not by using any chemical, right. We are applying here some potential on the electrode surface. We can apply some oxidation potential. Suppose we can apply some positive potential like 0.3 volt we can apply, so that it can release the electrons. So, it can release the electrons and it will form like its oxidized species. So, this is actually because we are oxidizing this one electrochemically. So, this is electrochemical oxidations. Okay. This is called electrochemical oxidation, and here reductions, but this is chemical reduction. This is chemical reductions, but here oxidations, and this oxidation is the electrochemical oxidations. So, by this way we can cyclically form this redox. See, this is consuming and then again reproducing, consuming again reproducing, right. This kind of cycling reactions can be possible on the surface, and it can be useful for signal amplification. So, I will show you some basic example like how we can use this one for biosensor development, that I can show you. So, this is a very basic sandwich biosensor that I taught you last class. Just I want to show you again. To like glucose, it will react with the glucose oxidase, form the gluconic acid, and so it is kind of oxidizing agent, right. And then we are using some electron mediator like ruthenium hexamin 3 plus, and that will reduce to ruthenium hexamin 2 plus based on this like oxidation, say the glucose oxidizing, it will be releasing the electron, that electron actually getting ruthenium hexamin 3 plus is getting, right, and from the ruthenium hexamin 2 plus. So, now we will again this one we will oxidize, right, on the surface we will oxidize it and it will release one electron. So, again that is I am saying. So, these oxidations again, what oxidation reaction this one? This is the electrochemical oxidation, right, electrochemical oxidation. Okay. And here this reaction is the enzymatic reactions. This ruthenium hexamin 3 plus we use at the very beginning at the starting reagent, and glucose also we use at the starting reagent. So, this ruthenium hexamin 3 plus actually cannot react faster with the glucose, but if we use glucose oxidase, then only this reaction can happen, means ruthenium hexamin 3 plus can form the ruthenium hexamin 2 plus. So, glucose oxidase necessary. How you will get the glucose oxidase? If your sensor surface already have the target, this is the target. So, then secondary antibody can only bind. If it has target, only secondary antibody will bind and glucose oxidase may come on the surface. So, it is totally proportional to the target concentrations, right. If you have more target on the surface, means more glucose oxidase may come on the surface, because the secondary antibody will bind on the target. So, more glucose oxidase will react, and this reductions from ruthenium hexamin 3 to ruthenium hexamin 2 will be faster, right. So, many ruthenium hexamin 3 plus will form many ruthenium hexamin 2 plus. So, then this electron transfer rate, this oxidation, the electrochemical oxidation rate will be increased, right. So, because number of ruthenium hexamin 2 plus concentrations will be increased, naturally you will get the more current, right. So, like this way we can determine the concentrations of the target, right. So, if we get like this way, so there is some output, like if we can measure some that different technique I will teach you again after some class. So, like I just for example, if you want to measure, right, just current we want to measure with respect to time. So, if you have the less concentration ruthenium hexamin 2 plus, suppose you are getting this much current, and now if you more target with more glucose oxidase and more ruthenium hexamin will form, then we will get the more current. So, you can see the difference between the low concentration glucose oxidase, high concentration glucose oxidase. So, easily we can compare the number of target present on the surface. So, it will help you to predict the number of target. So, that again I will teach you when I will teach you this kind of technique. This is called actually chronoamperometry, this technique that I will teach you after some class, like which technique we can use for biosensor, this kind of signal detections. Okay. So, now it is pretty clear, the reducing agent, oxidizing agent, and we are applying some oxidation potential, right. So, here ruthenium we are using as a mediator, and what is the starting material. So, that is I told you, right, and this is the redox cycling happening in between on the surface, and this is the actually enzymatic redox cycling, right, that I told you also in the last class. Now, I will come to another example, right. See this example, like not only the one cycle, like in the previous slide I told there is one cycle, right, ruthenium hexamine 3 plus form the ruthenium hexamine 2 plus, and this cycling happening, and you will get the signal amplifications. But we can amplify this better way if we can incorporate one more cycle. See, here you can see in this scheme. So, CTNI means carbonic troponin I, this is just a target. So, if you have this target, then secondary antibody can bind, and secondary antibody, this IgG actually we conjugate it with a enzyme that is called ALP, alkaline phosphate. Okay. So, if in your sensor surface, if you have target, then this secondary antibody will bind, right, that just I told you. Now, for this enzyme we need a substrate, right, because enzyme will not directly participate in the redox cycling. So, some electron, so you can say that some active material will form by using this enzyme, and that material will take part in the redox cycling. Okay. So, we will use a substrate like APP, alkaline phosphate, and this one aminophenyl. This is just a substrate for ALP. Now, when this substrate will react with ALP, it will form the AP. AP is the aminophenol. Aminophenol. So, this is aminophenol. It can read easily. It can form quinonimine, dol 1 NH, or maybe it is sometimes it is the intermediator. Sometimes it can form like this quinone. So, this is the electron transfer process, like it can release one electron, it can get one electron, and this kind of redox reactions can happen. So, this is a highly active species. So, this ALP basically helping from APP to generate a highly electroactive species. So, AP here highly electroactive species, but APP no, it is not a highly electroactive species. Okay. So, in this scheme, now you have to tell, right, what is the starting material, right. So, AP should not be starting material if it is the starting material for this biosensor. Starting material means that I told, no, like you have to think about signal to background ratio. So, signal means in the presence of target, right. So, in the presence of target, then ALP present, then APP will react, then AP will form, and then this reaction will start, that is signal. So, this all the reaction corresponds to the signal reactions. And what is the background? Background means if you do not have this target, this target you do not have, then if there is no target, no ALP, right. If no ALP, then no AP, AP will not form. So, if no AP, then these reactions will not happen, ruthenium hexamine 3 to 2. So, this all the reaction will not happen on the surface. So, your starting agent in the case of background, what is your starting reagent in this biosensor scheme? APP, because ALP not there, say APP, and this T-shape you are using is a reducing agent. So, only in the presence target AP will form. So, then think which one will be your starting agent? 1 APP, 2 T-shape, and 3 your ruthenium hexamine 3 plus. These 3 will be your starting agent. Clear? So, your background should be very low in this biosensor. Okay. So, let us remove again everything. So, I am just removing so that I can show you again all the background signal. So, just keep in mind that your background signal should be very, very low to design a ultrasensitive biosensor. So, in this case, as I told, your starting agent APP, T-shape, ruthenium hexamin 3 plus. So, naturally, if you want to get low background current, so these starting agent 1, 2, 3, they should not react each other. If they react each other means they will generate the high signal. So, if you want to get low background and high signal, then these two should react very, very slow. Their kinetics, reaction kinetics should be very, very slow. One thing, these three together, or you can think like separately also, even ruthenium hexamin 3 plus at the starting it present, because at the end of the reaction scheme I will show you that we are applying here some potential, suppose 0.3 volt we are applying, right, from the outside. So, when you apply some potential, in that potential this starting region also can be oxidized on the surface. So, they should not also oxidize very fast on the surface, right, then only we can generate very low background current. So, ruthenium so I can draw now like ruthenium hexamin 3 plus, it should not release the electron very fast. I think you know also ruthenium hexamin 3 to 4, this is also not favorable process. So, anyway, so this reaction rate will be very, very low because this is not favorable process. And T-shape, see, T-shape also can be oxidized on the surface, right, that is also your starting agent. T-shape can be oxidized, T-shape O, because it is reducing agent. So, it can also easily oxidize, but it should not generate, it should be very, very slow, or they should react or no reaction almost. This electron release almost it should be stopped. If it is slow, then it is very good sensor. Okay. So, this is also should be slow process. Another APP, this is also starting agent here. So, your sensor surface, your APP also should not react. So, these conditions you have to keep in mind to get low background current. And you are using these three mixture actually on the sensor surface, right. So, you are using T-shape plus APP plus ruthenium NH3 whole 6 3 plus, right, here oxidation state 3. So, you are taking this one in a sample tube, right, then you are putting on the sensor surface. So, there should not be any chemical reactions also, right, in this mixture no chemical reaction should happen, otherwise the chemical they can change and they can behave something different. So, you may get some current, right. So, that also you should keep in mind, they should not chemically also they should not react. Okay. So, then if this satisfy, then your background will be very, very low, right, your background will be very, very low. And let us get to the signal part. So, your signal part is ALP there because your target there, ALP there, APP reacting with the ALP and AP form. So, this AP is highly electrochemically active. Immediately AP will react with ruthenium hexamin 3 plus. So, you have to keep in mind, let us erase again everything here. So, what is the signal part, right? So, which part there should be the high reactions and which part there should be the very, very low reaction rate. Okay. Okay, let us show you here now. So, this AP and ruthenium hexamin 3 plus, so they should react very fast, right. Then only ruthenium hexamin 3 plus can generate ruthenium hexamin 2 plus very easily, because this will finally will oxidize on the surface, it will generate the electron, you will get the current. So, this reaction should be very, very fast. And when AP react with ruthenium hexamin 3 plus, it form the oxidized species quinonimine. So, this quinonimine should reduce to aminophenol immediately. Why? Because then again aminophenol can react with ruthenium hexamin 3 plus, so that this cycle will be very fast. So, quinonimine plus T-shape, this reaction should be very fast. So, you have to choose. So, I am telling this as generic idea. So, even you can change this reducing agent, you can change reducing agent, you can change something else also. Instead of using APP something different, ALP has so many substrate, you can use something different substrate, you can produce the another electroactive species. So, you can optimize which reducing agent is the best, which substrate is the best, that we can optimize. Then we can get the best redox cycling method. So, in this redox cycling case, we found that quinonamine can easily form aminophenol with T-shape. That is why we choose the T-shape. But there is some other reducing agent also present, like sodium borohydride, that also you can try. So, lots of scope also there. Okay. So, this process done. Now, as you seen here, you have seen that ruthenium hexamine 3 plus already formed ruthenium hexamine 2 plus. So, ruthenium hexamine 2 plus should react on the electrode surface very fast, because this is the final species that we are going to oxidize on the surface, right. So, this should be react on the surface very fast. If ruthenium hexamine 2 plus itself, if its reaction means electrochemical oxidation reaction is very slow, then you will get the lower current, your signal will not be very high. So, you will get very high signal if your ruthenium hexamine 2 plus will oxidize on the sensor surface very fast. So, this reaction should be again very fast, clear. So, these things just you have to keep in mind, which electron mediator you will use. Here I use ruthenium hexamine 3 plus, maybe you can try something else also. If you see like periodic table in the same, there is the osmium also. So, osmium 2 plus, osmium 3 plus, this redox couple also we can try. Let us see if they are showing the high amplification or lower amplification by comparing this, then you can try which one is the best. So, just this is the example, but you have lots of scope, you can change also by using different chemical. So, it is that's why I am saying it is just a generic concept, but you can change any chemical you can try. There is still scope, like you can change the substrate, you can change the reducing agent, you can change the mediator, and you can get the best one. And another thing, so here as I am always saying, we have to apply some potential, like finally, suppose you are applying 0.3 volt, but you can apply 0.4 volt, you can apply 0.5 volt, 0.1 volt, but which potential is the best to oxidize this ruthenium, that also we can optimize. So, which potential we can apply. Like this way, we can predict that this redox cycling is the best or not. So, you can find out the best redox cycling, and that you can try for your target or biomarker detections. Okay. So, this is one example, that is why I am just describing you very clearly, so that you can understand all the steps. So, in this picture I think it is very clear that I describe everything, that how we can design a redox cycling and how we can change the material. So, that the T-shape structure you know. Now, let us come here. So, see in the previous slide you have seen that ALP I used as a tag. This slide I am showing you here that in the last slide you have seen the tag is the ALP, but here I am using gold nanoparticle. AU means gold nanoparticle. So, here I am using the gold nanoparticles as the tagging agent. Here its role similar like ALP, but it is non-enzymatic material, right. So, this is the utility here, that we can use some nanomaterial also as a tag that can help to generate the similar kind of signal. What is the utility? That we are not using here enzyme. So, it is non-enzymatic. It is non-enzymatic biosensor. So, what is the benefit? Because enzyme is the protein. So, if you want to develop a point of care device, so sometime you have to store your sensor at the room temperature, the high temperature. So, at that temperature, as enzyme is protein, can be denatured easily, your sensor may not work. So, there is some drawback using the enzyme. And what is the benefit of using enzyme? Because enzyme is very specific, that is the utility of the enzyme, and reaction kinetics also very fast. But if you can eliminate the enzyme by a nanomaterial, that will be very good for your sensor design, because you can store it even at the high temperature. So, this non-enzymatic sensor will be very much useful for point of care device development. Okay. So, here I use the gold nanoparticle, and NP just a nitrophenol. NP means, so this is the nitrophenol. No, sorry, NP is the aminophenol, means NH2O is present, aminophenol we are using. So, this aminophenol, now aminophenol, okay, so let us clarify this one. This one aminophenol, and this NP is the nitro group, nitrophenol. So, this nitro group will be reduced to amine group. So, we need some reducing agent. Okay, we need some reducing agent. So, what is the reducing agent? Sodium borohydride. Basically, here NaBH4 can be used for a reducing agent, but for this nitrophenol, this one can be reduced to aminophenol in the presence of sodium borohydride, but we need a catalyst. This catalyst is the gold. If your sensor surface present gold nanoparticle, then only aminophenol will form, otherwise this aminophenol will not form. Okay. So, you need gold nanoparticle, mean this tag, like similar way, like previous case you need the ALP always, then only aminophenol will form. So, in this case you always need gold nanoparticle, then only sodium borohydride can reduce the nitrophenol to aminophenol. Clear? But this gold not directly participating in the redox cycling, just keep in mind this one not directly participating, it is forming a very active material, electroactive you can say, or maybe chemically active material it is forming, that is the aminophenol. It is very active, but nitrophenol is not active, right. So, in this case what is the starting material, then you can easily find out nitrophenol, NP is the starting material, sodium borohydride is the reducing agent, the starting material, and Fc plus. This is just like the ferrocins. So, I will show you here. Yes. So, you can see here ferrocins. So, this ferrocin is the starting material. So, ferrocin is like the structure here. So, 5-member ring and irons here, the you can see the iron. So, this is actually we are using as the starting material. So, naturally they should not, so ferrocin plus, as I said before, like this ferrocin plus nitrophenol, sodium borohydride, they should not react because they are causing the background current. Clear? And as in the presence of gold nanoparticle aminophenol form, so aminophenol should react very fast with the ferrocin and it will form the ferrocin 0, and it can react easily on the sensor surface, it will generate the electron, that is the very fast electron transfer. And ferrocin plus should not react the sodium borohydride, this reaction should be slow, but this sodium borohydride should react with the quinonimine very fast, so that aminophenol will regenerate again. See, so in the previous slide I showed only you can, if you go back to the previous slide, let us see. So, here like 2 cycle, here 1 cycle. So, but here you can see again the 2 cycle, like here 1 cycle, here 1 cycle, like 2 cycle. So, more cycle means that electron transfer rate also will be very faster. Number of cycle can improve the electron transfer rate and your signal naturally will be very high. That is why sometimes we are incorporating more number of cycle to enhance the signal. Okay. So, these things that these things just you have to remember that how they are reacting. And another things here I just showing you, like methylene blue also can be used for the redox cycling reactions, but that I will teach you again in the next class. Methylene blue one kind of the chemical. So, this kind of also chemical also can be used for the redox cycling reactions, but that I will teach you again the next class. So, this is the utility, means I am teaching slowly like enzyme to non-enzymatic method, so that we can tag the antibody with some. Now, first I showed you enzyme, then I showed you nanomaterial, now I will show you with some chemical we can tag. Slowly we can increase the stability of the sensor. Okay. That I will show you slowly in the next class. So, the conclusion, so the enzymatic non-enzymatic biosensor, we can improve the stability with the signal amplification, so that we can use this one for biosensing applications. So, we can detect very low amount of biomarker. So, that is all for this class. Thank you. Next class I will teach you again this signal amplification.